Trigonometric substitutions. Alright, so now let's try a different type of example. Let's evaluate the integral of dx over the square root of x squared plus a squared. Alright, so this time what we have is an integral involving an expression of the form the square root of x squared plus a squared. Now this time my values for x can be anything. It can be positive, negative, there's no limit because this will always be positive and I'm adding a positive term to it. So since x can take on any value, what function can we use to represent it? Well, the function tangent takes on every value between negative and infinity exactly once on the interval minus pi over 2 to pi over 2. So what we're going to do is we're going to let x be equal to a times tangent of theta. So now that we've done that, let's go ahead and set up the substitutions we're going to make, and let's set up our reference triangle. So we get that x is equal to a tangent theta. That means that dx is equal to a times secant squared theta d theta. And that means if solving this for tangent theta here, that tangent theta is equal to x over a, well, tangent is opposite over adjacent. If we set up our reference triangle, here's our opposite, here's our adjacent. Using the Pythagorean theorem, we can find the length of the hypotenuse. And then one last thing we might want to know is what is theta equal to? Well, since tangent is defined on the interval minus pi over 2 to pi over 2, we can talk about the inverse function. So we get tangent inverse of x over a is equal to our theta. Alright, so now that we have this set up, let's evaluate our integral. Here's our integral. We go ahead and make the substitutions we talked about. We said dx was going to be equal to a secant squared theta d theta, and we were letting x be equal to a tangent theta. Just simplifying this a bit, changing this term here to a squared tangent squared theta. We now see under the radical, I can factor out an a squared. Once I've done that, I have a squared times tangent squared theta plus 1 right here. Well, tangent squared theta plus 1 is equal to secant squared theta. It's one of the Pythagorean identities. So now what we need to do is simplify this integral. And to do that, first we'll take the square root of a squared secant squared theta to get a secant theta in the denominator. And now we can cancel an a from the numerator and the denominator, and also secant theta. So we're left with the integral of secant theta. And by now, hopefully, you've memorized that the antiderivative of secant theta is equal to the natural log of secant theta plus tangent theta plus c. Alright, so now we found the value of our integral, but it's in terms of theta. We need to put it in terms of x. To do that, we go back to look at our reference triangle. So here's our information from our reference triangle. We said x was equal to a tangent theta was equal to x over a, and from that we got our reference triangle. And what we needed to know was what secant of theta was. Well, secant is equal to hypotenuse over adjacent, so we see that secant theta is equal to the square root of x squared plus a squared all over a. So, plugging that in, we get that this integral, which we said was equal to the natural log of secant theta plus tangent theta plus c, now becomes the natural log of secant theta we said was the square root of x squared plus a squared all over a, and we said tangent theta was x over a plus c. So this is great. We found our solution. It's in terms of x, but we can make it look a little bit better. And the way we can do that is, notice these are both over a, so we can put them over a common denominator. And then we can use our properties of logarithms to rewrite the right-hand side of this equation as follows. This is going to be equal to the natural log of our numerator minus the natural log of our denominator plus c. And when we do that, this natural log of a here That's just a constant. There's no variables in there. Remember, a is a constant. So that can be absorbed into our plus c to give us the natural log of the square root of x squared plus a squared plus x plus c. And one final thing we can do is notice this term in here, inside my natural log, is always going to be positive. The square root of x squared plus a squared is always going to be bigger than the absolute value of x. So that means this here is always going to be positive, so I can get rid of my absolute value signs to get my final answer, that the integral of 1 over the square root of x squared plus a squared is equal to the natural log of the square root of x squared plus a squared plus x plus c.